Hello there. I'm so glad you found your way here tonight. Wherever you are in the world tonight, allow yourself to settle into this shared moment of stillness. Let the noise of the day soften. Let your thoughts grow quiet, like starlight fading gently into the darkness between galaxies. Imagine drifting through the night sky, gliding past hidden planets, glowing stars, and ancient galaxies that have been shining since long before our world existed. Tonight we journey through the quiet wonders of the cosmos. There is no test waiting at the end. No rush. No urgency. Just the slow unfolding of the universe's most extraordinary secrets to carry you gently towards sleep. We will explore how space itself is expanding, how invisible matter holds galaxies together, how ancient light from the universe's first moments still fills every corner of existence, all of it waiting to be whispered into the stillness. Tonight, let's drift off together while exploring 100 soothing facts about the cosmos. There's no rush here, no test at the end, just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the vast universe that surrounds us. Either way, this space is for you. There is something deeply calming about contemplating the cosmos. Every star, every galaxy, every thread of the cosmic web carries within it a story billions of years in the making. You are part of that story. The atoms in your body were forged in ancient stars. The ground beneath you is made of stardust. The very light reaching your eyes tonight has been traveling through space for millions of years. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in. Let your breathing slow, and let the weight of the day drift away like starlight fading softly into the void. The cosmos is vast beyond imagination. It contains more stars than all the grains of sand on all the beaches of Earth. It stretches for billions of light years in every direction. And yet in all that immensity you are here. A warm presence in the darkness. A small but meaningful part of the cosmic story. Tonight, we will wander through this magnificent universe. We will meet forces that shape galaxies and powers that stretch across billions of light years. And we will discover truths about the cosmos that may surprise even the most curious minds. But there is no hurry. The universe has been unfolding for nearly 14 billion years. It can wait a little longer while you rest. Let us begin with the vastness of space itself. There are more stars in the universe than grains of sand on Earth. Astronomers estimate that the observable universe contains roughly 200 billion trillion stars. That number is so vast it defies comprehension. Scientists have compared it to the number of grains of sand on every beach and desert on our planet, and the stars still come out ahead. Each of those stars is a sun in its own right, many larger and brighter than our own. Some harbor planets. Some have already burned out. Others are still forming in distant nebulae. When you gaze at the night sky, you see only a tiny fraction of this cosmic multitude. The stars visible to the naked eye number merely a few thousand, yet behind each pinpoint of light lies a galaxy containing hundreds of billions more. The universe is populated beyond imagination, a sea of suns stretching endlessly into the dark. The observable universe stretches 93 billion light-years wide. When cosmologists speak of the observable universe, they mean the spherical region of space, from which light has had time to reach us since the Big Bang. This sphere has a diameter of approximately 93 billion light-years. The number seems paradoxical at first, since the universe is only about 13.8 billion years old. How can we see objects 93 billion light-years away? The answer lies in cosmic expansion. While light has been traveling toward us, the space through which it moves has been stretching. The galaxies that emitted that ancient light have since been carried much farther away by the expanding fabric of space-time. The observable universe is thus far larger than the distance light could travel in a static cosmos. Beyond its edge, more universe almost certainly exists, but its light has not yet had time to reach our eyes. Beyond the observable universe, space may extend infinitely. The edge of the observable universe is not the edge of existence. It is simply the limit of what we can see. Beyond that cosmic horizon, space almost certainly continues, possibly forever. Some cosmological models suggest the universe is infinite in extent, with matter and galaxies stretching endlessly in every direction. Others propose that space curves back on itself like the surface of a sphere, finite, but without boundaries. We cannot know for certain, because no information from beyond the observable horizon can ever reach us. The light from those distant regions has not had enough time to travel here, and because space is expanding faster than light can cross it, that light may never arrive. What lies beyond remains one of the greatest mysteries in all of science, a question we may never be able to answer directly. The cosmic horizon limits what we can ever observe. The cosmic horizon represents the ultimate boundary of our observable universe. It marks the distance beyond which light has not had enough time to reach us since the beginning of the cosmos. This boundary is not fixed but grows slowly over time, as more light has the chance to arrive. However, because the universe is expanding at an accelerating rate, many distant regions are moving away from us faster than light can bridge the gap. These regions are receding beyond our horizon forever. Galaxies we can see today will eventually fade from view, as expansion carries them beyond the observable edge. The cosmic horizon is not a physical barrier, but a limitation imposed by the finite speed of light and the age of the universe. It reminds us that our view of the cosmos, however vast, is inherently incomplete. Light years measure distances too vast for ordinary units. A light year is the distance that light travels in 1 year, racing through the vacuum of space at nearly 300,000 kilometers per second. Over the course of a year, light covers approximately 9.5 trillion kilometers. This unit exists because cosmic distances are so immense that measuring them in kilometers or miles becomes absurd. Even the nearest star beyond our Sun, Proxima Centauri, lies over 4 light-years away. The center of our galaxy is about 26,000 light-years distant. The Andromeda Galaxy, our nearest large galactic neighbor, is roughly 2.5 million light-years from Earth. When we observe objects at such distances, we are also looking back in time. The light arriving from Andromeda tonight left its stars 2.5 million years ago, long before humans walked the Earth. The universe's shape is incredibly close to flat. When cosmologists speak of the shape of the universe, they are referring to its geometry on the largest scales. Space can curve in different ways, depending on the density of matter and energy it contains. If the universe had more than a critical density, space would curve back on itself like a sphere. If it had less, space would curve outward like a saddle. Observations of the cosmic microwave background and the distribution of galaxies suggest that the universe is extraordinarily close to flat, meaning parallel lines remain parallel over cosmic distances. This flatness is so precise that scientists believe it cannot be coincidental. The theory of cosmic inflation explains this remarkable property by proposing that a brief period of exponential expansion in the early universe stretched any initial curvature to imperceptible levels. The Big Bang was not an explosion, but the creation of space-time itself. The common image of the Big Bang as an explosion in empty space is misleading. There was no pre-existing void into which matter burst forth. Instead, the Big Bang marked the beginning of space and time themselves. Before this moment, there was no before, because time itself did not exist. The Big Bang was the sudden emergence of the universe from an incomprehensibly hot and dense state, smaller than an atom. Space expanded from within, carrying matter and energy along with it. Every point in the universe was once the same point. The expansion did not happen at a particular location in space, because it was the expansion of space. This profound distinction transforms our understanding of cosmic origins. The Big Bang was not an event that happened somewhere in the universe. It was the event that created the universe. In the universe's earliest moments, space expanded faster than light. During the first fraction of a second after the Big Bang, the universe underwent a period of astonishing expansion known as cosmic inflation. In this brief epoch, space expanded exponentially, doubling in size again and again in an unimaginably short time. The expansion was so rapid that regions of space moved apart faster than light could travel between them. This does not violate relativity, because nothing was moving through space faster than light. Instead, space itself was stretching, carrying everything along with it. Inflation explains why distant regions of the universe look so similar, despite never having been in contact. Before inflation separated them, these regions were close enough to share energy and reach the same temperature. Inflation stretched this uniformity across the cosmos. Cosmic inflation stretched tiny quantum fluctuations to cosmic scales. In the quantum realm, nothing is perfectly still. Even empty space seethes with tiny fluctuations in energy that appear and vanish in instants. During cosmic inflation, these microscopic quantum ripples were stretched to astronomical sizes by the violent expansion of space. What began as subatomic wiggles became the seeds of all cosmic structure. These inflated fluctuations left their imprint on the distribution of matter and energy across the universe. Regions slightly denser than average would eventually collapse under gravity to form galaxies and clusters. The quantum world, normally hidden at scales far too small to see, thus left its fingerprints on the largest structures in existence. The galaxies we observe today are fossils of quantum mechanics, stretched across billions of light-years. Inflation explains why the universe appears smooth and uniform. When astronomers look in opposite directions across the sky, they see regions of space that have never been in causal contact. Light from one side has not had time to reach the other since the Big Bang. Yet these distant regions have nearly identical temperatures and densities. This cosmic uniformity puzzled scientists for decades. How could regions that never communicated end up so similar? Inflation provides the answer. Before the inflationary expansion, the entire observable universe was contained in a region small enough for light to cross easily. Energy could flow freely, temperatures could equalize, and matter could distribute evenly. Then inflation stretched this tiny uniform patch into the vast cosmos we see today. The smoothness we observe is a relic of that brief moment when everything was connected. Tiny fluctuations in the early universe seeded all cosmic structures. The universe we inhabit today, with its galaxies, clusters, and vast empty voids, traces its ancestry to minuscule density variations in the primordial plasma. These fluctuations were incredibly subtle, differing from the average density by only about 1 part in 100,000. Yet gravity amplified these tiny differences over billions of years. Regions slightly denser than their surroundings attracted more matter, growing denser still. Over cosmic time, this runaway process built the intricate web of galaxies we observe today. The largest structures in the universe, spanning hundreds of millions of light-years, are the descendants of quantum whispers from the first moments of existence. From almost nothing came everything, guided by the patient hand of gravity working across eons. Photons from the Big Bang carry messages from the universe's birth. Light created in the earliest moments of cosmic history still permeates all of space. These ancient photons were born in the hot plasma of the young universe, bouncing endlessly between charged particles in a cosmic fog. As the universe expanded and cooled, atoms formed and the fog cleared, releasing the light to travel freely. That light has been journeying ever since, its wavelength stretched by cosmic expansion into the microwave part of the spectrum. Today we detect it as the cosmic microwave background, a faint glow coming from every direction in the sky. Each photon in this ancient light carries information about the conditions of the universe when it was less than 400,000 years old. We are bathed in messengers from the dawn of time. Ancient light from the universe's earliest moments still fills all of space. Everywhere you look, the cosmos glows with ancient light. This radiation, known as the cosmic microwave background, pervades every corner of the observable universe. It is not concentrated in any particular direction, but comes uniformly from all around us, filling space like an invisible sea. The light was released when the universe was just 380,000 years old, a mere infant compared to its current age of nearly 14 billion years. Before that moment, the cosmos was an opaque plasma, where photons could not travel freely. When atoms finally formed, and the universe became transparent, this primordial light was set free to wander through space for eternity. We live immersed in this ancient glow, surrounded by the oldest light in existence. The cosmic microwave background captures a snapshot of the young universe. When scientists map the cosmic microwave background, they are essentially taking a photograph of the universe as it appeared nearly 14 billion years ago. This image shows the cosmos before any stars or galaxies existed, when matter was still spread almost uniformly throughout space. The tiny temperature variations visible in this ancient light reveal the seeds of all future structure. Regions slightly warmer or cooler than average correspond to areas that were marginally denser or less dense. These minuscule differences would eventually grow under gravity's influence into the galaxies and galaxy clusters we see today. The cosmic microwave background is the oldest photograph possible, capturing the universe in its infancy before the first lights were switched on. Photons last scattered about 380,000 years after the Big Bang. For the first few 100,000 years after the Big Bang, the universe was a blinding fog. Photons could not travel far before colliding with free electrons, scattering in random directions. Light was trapped, bouncing endlessly through the hot plasma that filled all of space. As the universe expanded and cooled, a crucial threshold was crossed. The temperature dropped low enough for electrons to combine with protons and form neutral hydrogen atoms. Suddenly, photons had nothing to scatter from. They were released to stream freely through space, beginning a journey that continues to this day. This moment of last scattering, roughly 380,000 years after the Big Bang, marks the origin of the cosmic microwave background we detect today. The universe's oldest light has a temperature just above absolute zero. When the cosmic microwave background was first released, the universe had a temperature of about 3,000 degrees, glowing orange like a cooling ember. Over nearly 14 billion years of cosmic expansion, the wavelength of this light has been stretched by a factor of more than 1,000. What was once visible light has shifted into the microwave region of the spectrum. Today, the cosmic microwave background has an effective temperature of just 2.7 degrees above absolute zero. This is colder than the darkest shadows of interstellar space, and only slightly warmer than the theoretical minimum temperature possible. Yet this faint warmth fills the entire universe, a whisper of heat from the cosmic dawn that still bathes every corner of existence. Tiny temperature differences in ancient light-seeded galaxies and clusters. The cosmic microwave background is remarkably uniform, but not perfectly so. Careful measurements reveal tiny temperature variations, differing from the average by only about 1 part in 100,000. These minuscule hot and cold spots correspond to regions of slightly different density in the early universe. Where the primordial plasma was marginally denser, gravity would eventually draw in more matter. Over billions of years, these subtle overdensities collapsed into galaxies, galaxy clusters, and the vast cosmic web. The temperature map of the cosmic microwave background is thus a blueprint for the universe's structure. Every galaxy, every cluster, every void can trace its ancestry back to these faint ripples in the ancient light. Polarization patterns in ancient light reveal the universe's earliest moments. Beyond temperature, the cosmic microwave background carries another layer of information in its polarization. Light waves can oscillate in different orientations, and the way these orientations are aligned across the sky encodes secrets about cosmic history. Certain polarization patterns, called E-modes, arise from the density fluctuations that seeded galaxies. Even more elusive are B-modes, which may carry signatures of gravitational waves generated during cosmic inflation. Detecting these faint swirls in the ancient light could provide direct evidence of the universe's exponential expansion in its first fraction of a second. Scientists around the world are building ever more sensitive instruments to read these subtle messages, hoping to glimpse the universe's birth hidden in the polarized glow. The discovery of cosmic background radiation confirmed the Big Bang. For decades, the Big Bang theory remained controversial. Some scientists preferred a steady-state model in which the universe had existed forever, with new matter continuously created to fill expanding space. In 1965, 2 radio astronomers accidentally discovered a persistent noise in their antenna that they could not eliminate. It came from every direction in the sky, at exactly the temperature predicted for the remnant glow of the Big Bang. This discovery, which earned Arno Penzias and Robert Wilson the Nobel Prize, transformed cosmology. The cosmic microwave background provided direct observational evidence that the universe began in a hot, dense state and has been expanding and cooling ever since. The debate was effectively settled. The Big Bang had left its fingerprint across the sky. Space itself is expanding, carrying galaxies farther apart every moment. The expansion of the universe is not like an explosion scattering debris through empty space. Instead, space itself is stretching, and galaxies are carried along like raisins in rising bread dough. The galaxies are not moving through space so much as space is growing between them. This expansion happens everywhere at once, affecting the fabric of the cosmos on the largest scales. Nearby galaxies are held together by gravity and do not feel this expansion, but distant galaxies are being carried away from us by the swelling of space between. The farther away a galaxy is, the faster it appears to recede. This is not because it is moving faster, but because more space exists between us, and all of it is expanding. The universe is literally growing larger with every passing moment. The Hubble constant measures the universe's current expansion rate. Named after Edwin Hubble, who first observed that galaxies are receding from us, the Hubble constant quantifies how fast the universe is expanding at the present time. It is typically expressed as about 70 kilometers per second per megaparsec, meaning that for every million parsecs of distance, galaxies appear to recede an additional 70 kilometers per second. Measuring this number precisely has been one of cosmology's great challenges. Different methods yield slightly different values, a discrepancy known as the Hubble tension that continues to puzzle scientists. The Hubble constant is not truly constant over cosmic time, having changed as the universe evolved. But at any given moment, it sets the rate at which space stretches and distances grow. The scale factor describes how distances in the universe grow over time. Cosmologists use a quantity called the scale factor to track how the universe expands. This dimensionless number represents the relative size of the universe at different epochs. If we set the scale factor to 1 today, it was smaller in the past and will be larger in the future. At the moment of the Big Bang, the scale factor was essentially 0. As the universe expanded, the scale factor grew, and all distances between galaxies stretched proportionally. By studying how the scale factor has changed over cosmic history, scientists can reconstruct the evolution of the universe and predict its future. The equations governing the scale factor depend on the contents of the universe, including matter, radiation, and dark energy. Expanding space stretches the light traveling through it. As photons journey across the cosmos, they are affected by the expansion of space itself. The wavelengths of light stretch along with the fabric of space-time, becoming longer as they travel. Light that started as energetic ultraviolet or visible radiation gradually shifts toward longer, redder wavelengths. Over vast cosmic distances and billions of years of travel, this effect becomes dramatic. Light from the most distant galaxies has been stretched so much that it arrives as infrared or even microwave radiation. This cosmological redshift is different from the Doppler effect of ordinary motion. It arises purely from the expansion of space during the light's journey. By measuring how much a galaxy's light has been stretched, astronomers can determine how much the universe has expanded since that light was emitted. As galaxies move away, their light shifts to longer red wavelengths. When astronomers observe distant galaxies, they find that the characteristic patterns of light emitted by atoms have all shifted toward the red end of the spectrum. This redshift is the signature of cosmic expansion. The more distant a galaxy, the greater its redshift, because more expanding space lies between us. Redshift has become one of the most powerful tools in cosmology, allowing scientists to measure distances and map the structure of the universe. By cataloging the redshifts of millions of galaxies, astronomers have constructed three-dimensional maps of cosmic structure, stretching back billions of years. Each redshifted photon carries information about how much the universe has grown since it began its journey toward us. Scientists use a step-by-step cosmic distance ladder to measure vast distances. Measuring distances in the universe is extraordinarily difficult because we cannot stretch a tape measure across billions of light-years. Instead, astronomers have developed a cosmic distance ladder, a series of techniques that build upon each other. Nearby distances are measured using parallax, the apparent shift of stars as Earth orbits the Sun. Further out, certain types of stars called Cepheid variables pulsate with a brightness related to their period, allowing their distances to be calculated. Still farther, Type Ia supernovae serve as standard candles, whose known luminosity reveals how far away they are. Each rung of the ladder calibrates the next, extending our reach across ever greater cosmic distances. This painstaking process has allowed us to map the universe out to billions of light-years. Invisible matter forms a hidden framework that holds galaxies together. When astronomers studied how galaxies rotate, they discovered something puzzling. The outer stars orbited far too quickly to be held by the gravity of visible matter alone. By all rights, these stars should have flown off into space, but they remained bound to their galaxies. Something unseen must be providing additional gravitational pull. This invisible substance came to be known as dark matter. It does not emit, absorb, or reflect light, making it impossible to observe directly. Yet its gravitational effects are unmistakable. Dark matter forms vast halos around galaxies, extending far beyond the visible stars and gas. It creates an invisible scaffold upon which galaxies are built, a hidden framework that shapes the structure of the cosmos. Dark matter makes up about 85% of all matter in the universe. The ordinary matter we can see, the stars, planets, gas and dust, accounts for only a small fraction of the universe's total matter content. Dark matter outweighs visible matter by roughly 5 to 1. This means that most of the mass in every galaxy, every cluster, and the cosmos as a whole is invisible. We are surrounded by a substance we cannot see, touch, or detect, except through its gravitational influence. Despite decades of research, the true nature of dark matter remains unknown. It is not made of atoms or any known particles. Various candidates have been proposed, from exotic weakly interacting massive particles to primordial black holes, but none has been definitively confirmed. Dark matter remains one of the deepest mysteries in physics. We detect dark matter only through its gravitational effects. Since dark matter neither emits nor absorbs light, we cannot see it directly with any telescope. The only way we know it exists is through the gravity it exerts on visible matter and light. Galaxies rotate too fast, galaxy clusters weigh too much, and light bends more than it should around massive objects. All these observations point to the presence of invisible mass. Physicists have built detectors deep underground, hoping to catch dark matter particles colliding with ordinary atoms, but so far none has succeeded. Particle accelerators have searched for dark matter production without success. The gravitational evidence for dark matter is overwhelming, yet the particles themselves remain elusive. They interact so weakly with ordinary matter that trillions pass through your body every second without leaving a trace. Galaxies are connected by vast webs of dark matter. On the largest scales, the universe is not a random scattering of galaxies, but an intricate network of filaments and voids. Dark matter forms the backbone of this cosmic web, with ordinary matter tracing its invisible structure. Galaxies and clusters condense at the nodes and along the filaments where dark matter is densest. Between these structures lie vast voids, nearly empty regions where dark matter is sparse. Computer simulations of cosmic evolution show dark matter collapsing under gravity, forming this web-like pattern over billions of years. The visible galaxies we observe are merely the bright decorations on a hidden scaffold of dark matter that spans the entire observable universe. Without dark matter, galaxies would not have enough mass to hold together. The visible matter in a galaxy, all its stars and gas, provides only a fraction of the gravitational pull needed to keep the galaxy from flying apart. Stars in the outer regions orbit at speeds that should send them spinning off into intergalactic space, if only visible matter were present. Dark matter provides the additional gravity that holds galaxies together. It forms enormous halos surrounding each galaxy, extending far beyond the visible disk of stars. Without this invisible mass, the galaxies we see would never have formed in the first place. The gentle pull of dark matter gathered primordial gas into the first proto-galaxies. We owe our existence to a substance we have never directly observed. A mysterious force is pushing the universe's expansion to speed up. For most of cosmic history, the expansion of the universe was slowing down. Gravity, pulling matter together, acted as a brake on the expansion. Scientists expected this deceleration to continue indefinitely. But in 1998, observations of distant supernovae revealed something astonishing. The expansion of the universe is not slowing down but speeding up. Some unknown force is counteracting gravity and pushing galaxies apart at an ever-increasing rate. This discovery was so unexpected that it won its discoverers the Nobel Prize and transformed our understanding of cosmology. The cause of this accelerating expansion has been named dark energy, but the name conceals our profound ignorance. We do not know what dark energy is, only that it exists and dominates the fate of the cosmos. Dark energy makes up nearly 70% of the universe's total energy. When cosmologists tally up everything in the universe, dark energy dominates the ledger. It accounts for approximately 68% of the total energy content of the cosmos. Dark matter contributes about 27%, leaving ordinary matter with a mere 5%. The atoms that make up stars, planets, and everything we can see constitute only a small fraction of what exists. Most of the universe is made of substances we cannot directly observe or fully understand. Dark energy is the largest component, yet also the most mysterious. It permeates all of space uniformly and does not dilute as the universe expands. Unlike matter or radiation, its density appears to remain constant over cosmic time. Dark energy acts like a repulsive pressure pushing galaxies apart. Unlike ordinary matter and energy, which exert gravitational attraction, dark energy creates a kind of repulsive pressure that pushes space itself to expand faster. In Einstein's equations of general relativity, energy density contributes to gravity, but pressure also plays a role. Dark energy has negative pressure, meaning it pushes rather than pulls. This strange property causes space to stretch at an accelerating rate, carrying galaxies ever farther apart. The effect is negligible on small scales, where gravity dominates, but on cosmic scales it is the most powerful force in the universe. As the cosmos continues to expand, dark energy becomes ever more influential, while the density of matter steadily decreases. Understanding dark energy is crucial to predicting the fate of the cosmos. The ultimate destiny of the universe depends on the nature of dark energy. If dark energy remains constant, the universe will continue expanding forever, with galaxies drifting apart until they vanish beyond each other's horizons. Stars will burn out, black holes will evaporate, and the cosmos will fade into cold darkness. If dark energy grows stronger over time, it could eventually tear apart galaxies, stars, planets, and even atoms, in a scenario called the Big Rip. Alternatively, if dark energy weakens or reverses, the universe might collapse back upon itself in a big crunch. Our cosmic fate hangs on the behavior of a force we barely understand. Deciphering dark energy is one of the most important tasks facing physics today. The nature of dark energy remains one of science's greatest mysteries. Despite decades of research, scientists still do not know what dark energy actually is. The simplest explanation is that it represents the energy of empty space itself, a cosmological constant built into the fabric of the universe. But when physicists try to calculate this vacuum energy from quantum theory, they get an answer absurdly larger than what is observed. Other theories propose that dark energy is a dynamic field that evolves over time, or that our understanding of gravity itself is incomplete on cosmic scales. New telescopes and surveys are mapping the expansion of the universe with unprecedented precision, hoping to distinguish between these possibilities. For now, dark energy remains a profound enigma at the heart of cosmology. Giant filaments of matter connect clusters of galaxies like a cosmic web. On the largest scales, matter in the universe is not randomly distributed, but organized into an intricate pattern of filaments and nodes. These cosmic filaments are immense structures stretching hundreds of millions of light-years, connecting galaxy clusters like threads in a vast three-dimensional web. The filaments are composed primarily of dark matter, with ordinary matter tracing along their lengths. Hot gas fills the filaments, and galaxies cluster along them like beads on a string. Between the filaments lie enormous voids, regions almost completely empty of galaxies. This cosmic web is the largest known structure in the universe, a pattern that emerged from tiny density fluctuations in the early cosmos and was sculpted by gravity over billions of years. The cosmic web structure influences how galaxies grow and evolve. Galaxies do not exist in isolation. Their fates are shaped by their position within the cosmic web. Galaxies in dense filaments experience frequent interactions with neighbors, triggering bursts of star formation and fueling growth. Those falling into massive clusters may be stripped of their gas, halting star formation and transforming them from active spirals into quiescent ellipticals. Galaxies in voids evolve more peacefully, with fewer disturbances, but also less new material to fuel growth. The cosmic web acts as a highway system for matter, channeling gas flows and directing galaxy mergers. Understanding this environmental influence is essential to explaining the diverse population of galaxies we observe. Galaxies flow along gravitational currents shaped by matter's distribution. Just as rivers flow downhill toward the sea, galaxies drift along gravitational gradients created by the uneven distribution of matter. Regions of higher density exert stronger gravitational pull, drawing in nearby galaxies and causing them to stream toward massive clusters and filaments. These coherent flows are called peculiar velocities because they represent motion beyond the smooth expansion of the universe. Mapping these flows reveals the hidden distribution of matter, including dark matter that cannot be seen directly. Galaxy surveys have discovered large-scale flows pointing toward enormous concentrations of mass, some so distant they lie beyond the observable horizon. The universe is a dynamic place, with matter constantly in motion toward the densest regions of the cosmic web. Cosmic filaments contain much of the universe's ordinary matter. For years, astronomers could not account for all the ordinary matter predicted to exist in the universe. Stars, galaxies, and detected gas fell short of the total expected from Big Bang nucleosynthesis. Much of this missing matter has been found hiding in the filaments of the cosmic web. The gas between galaxies, heated to millions of degrees by gravitational collapse and shock waves, emits faint X-rays that have now been detected. This warm, hot intergalactic medium fills the filaments, accounting for a substantial portion of the missing baryons. The universe's ordinary matter was never truly missing, just spread thinly through the cosmic web in a form difficult to observe. Massive galaxy clusters form the densest nodes of the cosmic web. At the intersections of cosmic filaments, where multiple streams of matter converge, lie the most massive structures in the universe. Galaxy clusters contain hundreds or even thousands of galaxies, bound together by gravity, along with vast quantities of hot gas and dark matter. The total mass of a large cluster can exceed 1,000,000,000 times the mass of our Sun. These clusters are cosmic crossroads, drawing in galaxies from the surrounding filaments. The hot gas between cluster galaxies shines brightly in X-rays, while the dark matter can be mapped through its gravitational lensing of background light. Clusters serve as laboratories for studying dark matter, galaxy evolution, and the large-scale structure of the universe. Vast empty spaces known as voids stretch across millions of light-years. Between the filaments and clusters of the cosmic web lie enormous regions, almost completely devoid of galaxies. These cosmic voids are not merely empty spaces, but vast bubbles of underdensity that can span hundreds of millions of light-years. The largest known voids are so immense that light takes hundreds of millions of years to cross them. Within a void, the density of matter is far below the cosmic average, and galaxies are exceedingly rare. These empty regions are not static but slowly expand as matter continues to drain toward the surrounding filaments. Voids occupy most of the volume of the universe, making the cosmos more emptiness than substance. Cosmic voids are giant empty regions between galaxy clusters. When astronomers map the distribution of galaxies, they find that galaxies are not scattered evenly throughout space. Instead, they cluster along walls and filaments surrounding enormous empty bubbles. These voids are the great emptinesses of the universe, regions where matter is thin and galaxies are scarce. The boundaries of voids are marked by sheets and filaments of galaxies, creating a foam-like structure on cosmic scales. Each void is surrounded by walls of light, while the interior remains dark and lonely. The few galaxies that exist within voids tend to be small, isolated, and undisturbed, evolving slowly in splendid cosmic solitude. Though nearly empty, voids influence the movement of galaxies around them. Despite their emptiness, cosmic voids exert a subtle gravitational influence on their surroundings. The underdensity of a void creates a kind of repulsive effect, pushing galaxies away from its center and toward the surrounding walls. This effect is not true repulsion, but simply the result of the surrounding overdense regions pulling harder. Galaxies near the edges of voids are accelerated outward, while those in filaments are drawn inward. The expansion of the universe proceeds slightly faster within voids, because there is less matter to slow it down. Voids thus play an active role in shaping the dynamics of the cosmic web, despite containing almost nothing at all. Voids shape the large-scale structure of the universe. The cosmic web is defined as much by its emptiness as by its fullness. Voids carve out the spaces between filaments and clusters, determining the overall architecture of the universe. As the cosmos evolves, voids grow larger, while filaments and walls become thinner. The gravitational competition between overdense and underdense regions drives the evolution of cosmic structure. Eventually, voids may merge to form even larger empty regions, while matter concentrates into an ever-sparser network. Understanding the size, shape, and distribution of voids provides insight into the history of cosmic expansion and the forces that shaped the universe we see today. Studying voids helps scientists understand dark energy and matter distribution. Cosmic voids are surprisingly useful laboratories for cosmology. Because they are dominated by dark energy rather than matter, the expansion of space within voids is particularly sensitive to the properties of dark energy. By measuring how voids grow and how galaxies move around them, scientists can test different models of dark energy. Voids also provide a cleaner environment to study the relationship between galaxies and dark matter, free from the complicated interactions that occur in dense clusters. The statistical properties of void sizes, shapes, and distributions constrain our models of cosmic evolution. In emptiness, we find clues to the fundamental nature of the universe. The first stars ended the universe's long, dark silence. After the cosmic microwave background was released, the universe entered an era known as the Dark Ages. No stars yet existed, and the cosmos was filled only with neutral hydrogen and helium cooling in the darkness. This epoch lasted for roughly 100 million years, a vast stretch of cosmic history with no sources of light. Then, slowly, gravity drew matter together into the first dense clumps. Within these primordial clouds, temperatures and pressures rose until nuclear fusion ignited. The first stars blazed into existence, ending the cosmic dark ages and beginning a new chapter in the history of the universe. Light returned to the cosmos, and it has never been extinguished since. The universe's first stars were nearly pure hydrogen and helium. The Big Bang produced only the lightest elements: hydrogen, helium, and trace amounts of lithium. When the first stars formed, this was all the raw material available. These primordial stars, often called population 3 stars, contained virtually no heavier elements, because none yet existed. This pristine composition affected their properties profoundly. Without heavier elements to carry away heat through radiation, the gas clouds that formed these stars could not fragment easily. The resulting stars were likely enormous, perhaps hundreds of times the mass of our Sun. No population 3 stars have ever been directly observed, as they burned out long ago, but their legacy lives on in the heavy elements they created. These ancient stars burned hotter and faster than most stars today. The first stars were giants, far more massive than typical stars in the present universe. Their enormous mass meant they burned through their nuclear fuel at a furious rate, living fast and dying young. While our Sun will shine for about 10 billion years, these primordial behemoths exhausted their fuel in just a few million years. Their cores reached temperatures and pressures that forged elements heavier than hydrogen and helium for the first time. When they died in spectacular supernovae, they scattered these newly minted elements into space, seeding the cosmos with the raw materials for future generations of stars and planets. Everything we are made of was forged in stars like these. The first galaxies formed during an era known as cosmic dawn. As the first stars ignited, and their light began to spread, the universe entered a transformative era called cosmic dawn. Gravity continued to gather matter into ever larger structures, and the first stars clustered together into primitive galaxies. These early galaxies were small and irregular, nothing like the grand spirals we see today. They were factories of star formation, producing new generations of stars, enriched with the heavy elements created by their predecessors. Cosmic dawn marked the transition from a dark, featureless universe to the structured cosmos of galaxies and stars we observe today. It was the universe's awakening, the moment when light truly began to fill the void. The universe became transparent when ultraviolet light ionized hydrogen gas. During the Dark Ages, the universe was filled with neutral hydrogen atoms that scattered light and made space opaque to certain wavelengths. As the first stars and galaxies formed, they poured intense ultraviolet radiation into their surroundings. This energetic light ionized the neutral hydrogen, stripping electrons from atoms and rendering the gas transparent. This process, called reionization, transformed the universe from a foggy medium into the clear expanse we observe today. Reionization did not happen all at once, but spread outward from sources of light in growing bubbles that eventually merged. By about 1 billion years after the Big Bang, the universe was fully ionized, and light could travel unimpeded across cosmic distances. The first quasars ignited during the epoch of reionization. As galaxies grew and merged, some developed supermassive black holes at their centers. When gas fell into these black holes, it formed swirling accretion disks that released tremendous amounts of energy. The brightest of these objects, called quasars, shone with the luminosity of trillions of suns, outshining their entire host galaxies. The first quasars appeared during the epoch of reionization, contributing to the flood of ionizing radiation that cleared the cosmic fog. Observations of distant quasars have revealed the signatures of the reionization process, showing how the universe transitioned from opaque to transparent. These ancient beacons provide our clearest windows into the conditions of the early cosmos. Star formation peaked billions of years ago during cosmic high noon. The history of star formation in the universe follows a dramatic arc. In the early universe, star birth rates were modest as the first galaxies assembled. The rate of star formation then climbed steadily, reaching a peak about 10 billion years ago in an epoch astronomers call cosmic high noon. During this period, galaxies were forming stars at rates many times higher than today. Since then, the cosmic star formation rate has declined steadily as galaxies exhaust their supplies of cold gas. The universe today is far quieter than it was at its peak productivity. Most of the stars that will ever exist have already been born, and the cosmos is slowly fading toward a dimmer future. Elements heavier than helium grew more abundant as stars lived and died. The Big Bang created only the lightest elements, leaving the universe initially devoid of carbon, oxygen, iron, and the other elements essential for life. All heavier elements had to be forged inside stars through nuclear fusion. As stars burned through their fuel, they built up heavier nuclei in their cores. When massive stars exploded as supernovae, they scattered these elements into space. Each generation of stars was born from gas, enriched by the deaths of previous generations. Over billions of years, the abundance of heavy elements in the universe steadily increased. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were manufactured in stellar furnaces and distributed by cosmic explosions long before our solar system existed. Massive stars forged heavy elements and scattered them in supernovae. The most massive stars are cosmic alchemists, transmuting light elements into heavy ones through the intense pressures and temperatures in their cores. During their brief lives, they fuse hydrogen into helium, helium into carbon, and progressively heavier elements up to iron. When the core can no longer release energy through fusion, it collapses in a fraction of a second, triggering a supernova explosion. The tremendous energy of the collapse creates conditions extreme enough to forge elements heavier than iron, including gold, platinum, and uranium. The explosion flings these elements into space at thousands of kilometers per second. Supernovae are both destroyers and creators, ending stellar lives while seeding the cosmos with the ingredients for new worlds. Cosmic dust grains are the seeds from which stars and planets form. Scattered throughout interstellar space are tiny particles of solid matter known as cosmic dust. These grains are typically only a few micrometers across, composed of silicates, carbon compounds, and ices. They form in the outer atmospheres of dying stars and in the debris of supernovae. Despite their small size, dust grains play a crucial role in cosmic chemistry. Their surfaces provide sites where atoms can meet and form molecules, including complex organic compounds. When clouds of gas and dust collapse under gravity to form new stars, the dust grains clump together to build larger and larger bodies. Over time, these clumps grow into asteroids, comets, and eventually planets. Every world begins as a gathering of dust. Tiny grains of cosmic dust drift through space, playing vital roles. Cosmic dust may seem insignificant, but it influences nearly every aspect of galactic evolution. Dust absorbs and scatters light, dimming and reddening the appearance of distant stars and galaxies. It emits infrared radiation, allowing astronomers to trace regions of star formation hidden behind opaque clouds. Dust shields the interior of molecular clouds from harsh radiation, allowing complex molecules to form. It carries electric charges that interact with magnetic fields, affecting the dynamics of interstellar gas. Without cosmic dust, the universe would be a very different place. Stars might form differently, planets might not exist, and the chemistry of space would be far simpler. These tiny grains are essential threads in the fabric of the cosmos. Hidden behind cosmic dust, distant galaxies glow brightly in infrared light. Many of the most actively star-forming galaxies in the universe are shrouded in thick blankets of dust. Visible light from their young stars is absorbed by the dust and re-emitted at much longer infrared wavelengths. These dusty galaxies are nearly invisible to optical telescopes, but shine brilliantly in the infrared. Some of the most luminous objects in the universe fall into this category, their prodigious energy output hidden behind veils of dust. Infrared and sub-millimeter telescopes have revealed vast populations of these obscured galaxies, many of which were most active during cosmic high noon. Understanding these hidden systems is essential to completing our census of star formation across cosmic history. The Milky Way spins at over 500,000 miles per hour. Our home galaxy, the Milky Way, is not static but rotating. The entire disk of stars, gas and dust orbits around the galactic center at tremendous speeds. At our position about 26,000 light-years from the center, the Sun and its planets are traveling at roughly 220 kilometers per second, or about 500,000 miles per hour. Yet despite this incredible velocity, we feel nothing, because everything around us moves together. The stars, the clouds, the planets, all share the same orbital motion. Even at these speeds, the galaxy is so vast that one complete orbit takes approximately 250 million years. The last time the solar system was at this point in its galactic orbit, dinosaurs had not yet appeared on Earth. Our solar system orbits the galactic center once every 250 million years. The time it takes for the Sun to complete one orbit around the Milky Way is sometimes called a galactic year. At roughly 250 million Earth years per orbit, the solar system has completed only about 18 to 20 laps since its formation 4.5 billion years ago. In that time, Earth has seen the rise and fall of countless species, the assembly and breakup of supercontinents, and dramatic changes in climate and atmosphere. Each galactic year represents an almost inconceivable span of time, yet the galaxy has been spinning for far longer still. The Milky Way itself is about 13 billion years old, having completed dozens of rotations in its history. Sometimes galaxies collide and merge in slow dances lasting billions of years. Galaxies are not solitary wanderers, but members of groups and clusters where close encounters are common. When two galaxies pass near each other, their mutual gravity distorts their shapes, drawing out long tails of stars and gas. If their paths bring them close enough, they may merge entirely, their stars mingling over hundreds of millions of years. Despite the violence implied by words like collision, individual stars rarely crash into each other because the distances between them are so vast. Instead, galaxies pass through one another like ghosts, their stars weaving together in slow gravitational dances. The Milky Way itself is destined to merge with the Andromeda Galaxy in about 4 to 5 billion years, creating a new elliptical galaxy from the wreckage of two spirals. Galaxies grow bigger through slow mergers over billions of years. The grand galaxies we see today, with their billions of stars and sweeping spiral arms, were not born in their current form. They grew through a process of hierarchical assembly, starting as small clumps of stars and gas that merged to form larger systems. Over cosmic time, these mergers continued, building ever more massive galaxies. Small dwarf galaxies were absorbed by larger ones, adding their stars and dark matter to the growing whole. Even today, the Milky Way is consuming smaller satellite galaxies that ventured too close. The largest galaxies in the universe, the giant ellipticals found at the centers of clusters, grew to their enormous sizes by devouring countless smaller galaxies over billions of years. Our galaxy belongs to a massive supercluster containing thousands of galaxies. The Milky Way is not floating alone in space, but is part of a vast cosmic structure. We belong to the local group, a collection of more than 80 galaxies dominated by the Milky Way and the Andromeda Galaxy. The local group is itself part of the Virgo cluster, a larger assembly of over 1,000 galaxies. Beyond that, we are situated within the Laniakea supercluster, a region spanning 500 million light-years and containing over 100,000 galaxies. Laniakea means immense heaven in Hawaiian, a fitting name for a structure so vast it challenges comprehension. Our cosmic address extends far beyond our planet, our solar system, and even our galaxy. Gravitational tides stretch and shape galaxies over time. When galaxies pass near each other, their gravitational fields do not act uniformly. The side of a galaxy closer to its neighbor feels a stronger pull than the far side, creating a differential force called a tidal force. These tidal forces can stretch galaxies, drawing out long streamers of stars and gas that arc through intergalactic space. The iconic shapes of interacting galaxies, their bridges, tails, and distorted disks, are all consequences of tidal effects. Even our own galaxy bears the scars of tidal interactions. Streams of stars from disrupted dwarf galaxies loop around the Milky Way, remnants of ancient close encounters that tore apart smaller systems. Quasars shine as some of the brightest beacons from the distant past. Among the most luminous objects in the universe are quasars, intensely bright cores of distant galaxies powered by matter falling into supermassive black holes. A single quasar can outshine its entire host galaxy by a factor of 100 or more, blazing with the light of trillions of suns. Most quasars are found at great distances, meaning we see them as they were billions of years ago, when the universe was young, and black holes were growing rapidly. They serve as cosmic lighthouses, illuminating the conditions of the early universe. The light from quasars passes through intervening gas clouds, carrying information about the matter between us and these distant beacons. Quasars are powered by supermassive black holes consuming vast amounts of matter. At the heart of every quasar lies a supermassive black hole, millions or even billions of times the mass of our Sun. These black holes are surrounded by swirling accretion disks of gas and dust spiraling inward. As matter falls toward the event horizon, it is compressed and heated to extreme temperatures, releasing tremendous amounts of energy across the electromagnetic spectrum. The efficiency of this process is remarkable, converting a significant fraction of the infalling matter's mass into energy, according to Einstein's famous equation. Quasars can consume the equivalent of several Earth masses per second, and yet they can sustain this feeding frenzy for millions of years. High-energy X-rays glow from distant black holes, devouring matter. The regions closest to supermassive black holes are among the most extreme environments in the universe. Here, matter swirls at nearly the speed of light, heated to temperatures of millions of degrees. At these temperatures, the accretion disk glows brilliantly in X-rays, revealing the presence of the black hole to telescopes sensitive to high-energy radiation. X-ray observations have identified millions of active galactic nuclei across the sky, many of which are obscured at optical wavelengths by surrounding dust. These observations have shown that supermassive black holes are common at the centers of galaxies, and that their growth is intimately connected to the evolution of their host galaxies. Powerful jets of particles shoot out from supermassive black holes. Some supermassive black holes launch narrow beams of particles and energy that stream outward at nearly the speed of light. These relativistic jets are among the most energetic phenomena in the universe. They emerge perpendicular to the accretion disk, channeled by intense magnetic fields that twist and focus the outflow. The jets can extend for millions of light years, far beyond the boundaries of their host galaxies. They carry enormous amounts of energy into the surrounding intergalactic medium, heating gas, and influencing the formation of stars in nearby galaxies. The mechanism that produces these jets is still not fully understood, but it involves the interplay of gravity, rotation, and electromagnetism near the black hole's event horizon. Jets from black holes can stretch for millions of light years. The relativistic jets launched by active black holes are among the largest coherent structures in the universe. Some jets extend for millions of light years, dwarfing the galaxies that host them. As the jets travel through space, they inflate enormous lobes of radio-emitting plasma that can span entire galaxy clusters. The energy transported by these jets is staggering, equivalent to billions of supernovae released over millions of years. When jets interact with their surroundings, they create shockwaves that heat gas and can either trigger or suppress star formation in nearby galaxies. These cosmic fire hoses demonstrate the profound influence that supermassive black holes exert on their environments. Black hole jets sculpt their host galaxies by regulating star formation. The energy released by active black holes does not simply escape into the void. It interacts with the gas in and around the host galaxy, profoundly affecting its evolution. Jets and radiation from the black hole can heat surrounding gas, preventing it from cooling and collapsing to form new stars. This feedback process helps explain why the largest galaxies have stopped forming stars, despite containing vast reservoirs of gas. Without black hole feedback, galaxies would convert all their gas into stars far too quickly, producing systems much brighter than those we observe. The connection between black holes and their host galaxies suggests that they evolved together, each shaping the other over cosmic time. Nearly invisible neutrinos pass through everything all the time. Neutrinos are among the most elusive particles in the universe. They have no electric charge and interact only through the weak nuclear force and gravity, meaning they can pass through ordinary matter almost without notice. A neutrino can travel through a light year of solid lead with only a 50% chance of being stopped. This ghostly behavior makes them extraordinarily difficult to detect. Every second, trillions of neutrinos stream through your body, yet you are completely unaware of their passage. They are produced in vast quantities by nuclear reactions in the Sun, by supernovae, and by the cosmic processes of the early universe. Neutrinos carry information from places and events that light cannot reveal. Trillions of neutrinos fly through your body every second. The Sun is a prolific source of neutrinos, producing them in the nuclear reactions that power its core. About 65 billion solar neutrinos pass through every square centimeter of your body every second. At night, when the Sun is below the horizon, these neutrinos simply pass through the entire Earth to reach you, barely slowed by the intervening rock and metal. Besides solar neutrinos, you are also bathed in neutrinos from distant supernovae, from the cosmic background left over from the Big Bang, and from nuclear reactors and natural radioactivity on Earth. You swim in an invisible sea of neutrinos, unaware of the constant ghostly traffic passing through you. A sea of ancient neutrinos fills space from the earliest seconds after the Big Bang. Just as the cosmic microwave background consists of photons released when the universe was 380,000 years old, a cosmic neutrino background exists from an even earlier epoch. Neutrinos decoupled from other matter when the universe was only about 1 second old, far earlier than the photons of the microwave background. These relic neutrinos have been traveling through space ever since, cooling as the universe expanded. Today they fill all of space with a temperature of about 2 degrees above absolute zero. Detecting these ancient neutrinos directly has so far proven impossible, because their energies are so low. Yet their gravitational effects influence the distribution of matter in the universe. Relic neutrinos have filled space since the universe was only 1 second old. The cosmic neutrino background is one of the oldest relics of the universe, predating even the cosmic microwave background by hundreds of thousands of years. These neutrinos froze out of equilibrium with other particles when the universe was only 1 second old, and temperatures were about 10 billion degrees. At that moment, the weak interactions that kept neutrinos coupled to other matter could no longer keep pace with the expansion of the universe. The neutrinos streamed freely, carrying information about the universe at an age when light itself was still trapped in the cosmic plasma. Detecting these ghostly messengers would open a window to the earliest moments of cosmic history. Neutrinos offer clues about the universe's very beginnings. Because neutrinos interact so weakly with matter, they can escape from environments where light is trapped. When a massive star collapses into a supernova, nearly all the energy is carried away by neutrinos rather than light. Detecting these neutrinos provides information about the collapsing core that photons could never reveal. Similarly, the relic neutrinos from the Big Bang carry imprints of conditions in the first second of cosmic history. Their mass, though tiny, affects the clustering of galaxies on large scales. Precise cosmological observations are beginning to constrain the sum of neutrino masses, turning the universe into a particle physics laboratory. Neutrinos connect the smallest scales of physics to the largest structures in existence. High-energy particles race through space at nearly the speed of light. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that travel through the universe at velocities approaching the speed of light. Some carry energies millions of times greater than anything achievable in human-made particle accelerators. These particles are accelerated by violent cosmic events, such as supernova explosions, black hole jets, and collisions between galaxy clusters. Once launched, cosmic rays wander through the galaxy, deflected by magnetic fields until they eventually strike the atmosphere of a planet or are absorbed by interstellar gas. The most energetic cosmic rays are extraordinarily rare, with only about 1 particle per square kilometer per century striking Earth. Yet these rare events carry more energy than a professional tennis serve compressed into a single atomic nucleus. Cosmic rays were first discovered over a century ago. In the early 20th century, scientists noticed that electroscopes slowly discharged, even when shielded from known radiation sources. In 1912, Austrian physicist Victor Hess carried electrometers aloft in balloon flights and discovered that the ionization rate increased with altitude. This could only be explained by radiation coming from space rather than from Earth. Hess had discovered cosmic rays, earning him the Nobel Prize in Physics. Since then, scientists have built increasingly sophisticated detectors to study these high-energy visitors from the cosmos. Cosmic rays have become a tool for understanding particle physics, astrophysics, and the extreme environments where they are born. Exploding stars launch particles speeding through space as cosmic rays. Supernova remnants are among the most important sources of cosmic rays in our galaxy. When a massive star explodes, the expanding shockwave accelerates particles to extreme energies through a process called diffusive shock acceleration. Particles bouncing back and forth across the shock front gain energy with each crossing, eventually reaching velocities close to the speed of light. The magnetic fields within the remnant help confine the particles long enough for this acceleration to occur. Observations of supernova remnants in gamma rays and radio waves have confirmed that particle acceleration is occurring. Most of the cosmic rays striking Earth's atmosphere were probably accelerated in the expanding shells of long-dead stars. Cosmic ray showers cascade through Earth's atmosphere constantly. When a high-energy cosmic ray strikes an atom in Earth's upper atmosphere, it triggers a chain reaction of particle collisions. The original particle shatters the target nucleus, producing a spray of secondary particles that in turn collide with more atoms. This cascade multiplies rapidly, creating a shower of billions of particles that spreads downward through the atmosphere. By the time the shower reaches the ground, it can cover several square kilometers. Detectors on Earth's surface can measure these extensive air showers to study the original cosmic ray. The atmosphere acts as a natural calorimeter, revealing the energy and composition of particles that originated in the most extreme environments of the cosmos. Cosmic rays might subtly influence Earth's weather and cloud formation. Some scientists have proposed that cosmic rays may affect Earth's climate by influencing cloud formation. The idea is that cosmic ray particles ionize air molecules in the lower atmosphere, creating seeds around which water vapor can condense into cloud droplets. More clouds would reflect more sunlight, cooling the planet. When the sun is active, its magnetic field deflects more cosmic rays away from Earth, potentially reducing cloud cover and warming the climate. While this hypothesis remains controversial, and the effects are likely small compared to other climate drivers, it illustrates the surprising connections between the cosmos and conditions here on Earth. The universe may influence our weather in ways we are only beginning to understand. Cosmic rays interact with the solar wind flowing from the sun. The sun continuously emits a stream of charged particles called the solar wind, which carries the sun's magnetic field throughout the solar system. This magnetic field deflects incoming cosmic rays, acting as a shield that modulates the cosmic ray flux reaching Earth. When the sun is more active, with more sunspots and stronger magnetic fields, fewer cosmic rays penetrate to the inner solar system. During solar minimum, when the sun is quieter, cosmic ray intensities increase. This 11-year cycle of cosmic ray variation has been observed for decades. Spacecraft, traveling beyond the Sun's influence, have measured the unshielded cosmic ray environment of interstellar space, finding intensities significantly higher than those experienced on Earth. Cosmic rays constantly bombard Earth's upper atmosphere from all directions. Earth is under continuous assault by cosmic rays arriving from every corner of the sky. Most cosmic rays come from within our galaxy, accelerated by supernova remnants and other energetic phenomena. The highest energy particles may originate from distant, active galaxies or other extragalactic sources. Because cosmic rays are charged particles, they are deflected by magnetic fields as they travel through space, scrambling their original directions. By the time they reach Earth, they appear to come uniformly from all directions, masking the locations of their sources. Only the most energetic cosmic rays, which are less deflected, retain some directional information that might point back to their origins. Cosmic rays occasionally cause mutations in DNA here on Earth. The secondary particles produced by cosmic ray showers can penetrate to the ground and even pass through our bodies. When these particles strike DNA molecules, they can cause damage that leads to mutations. Most such damage is repaired by cellular mechanisms, but occasionally a mutation persists and is passed on to daughter cells. Over geological time, cosmic ray-induced mutations have contributed to the genetic diversity that drives evolution. At high altitudes and in space, where cosmic ray exposure is greater, the mutation rate increases. Astronauts on long missions face elevated cancer risks from cosmic radiation. The universe reaches down and writes itself into our very genes. Gravity leaves its subtle marks on the ancient light we observe today. As light travels across the universe, it passes through regions where mass is concentrated. According to Einstein's general theory of relativity, mass warps the fabric of space-time, and light follows this curved geometry. The result is that light rays are bent as they pass near massive objects, an effect called gravitational lensing. This bending leaves subtle distortions in the images of distant galaxies, and in the cosmic microwave background itself. By measuring these distortions, astronomers can map the distribution of matter along the line of sight, including the invisible dark matter. The ancient light carries the gravitational fingerprints of every structure it has passed on its journey to our telescopes. Light traveling through space is gently warped by gravity of massive objects. Einstein predicted that gravity would bend light, a prediction spectacularly confirmed during a solar eclipse in 1919, when starlight was observed to curve around the Sun. On cosmic scales, this effect becomes a powerful tool. When light from a distant source passes near a massive galaxy or cluster, its path is bent, causing the source to appear in a different position, or even as multiple images. The intervening mass acts as a natural lens, magnifying and distorting the background light. This gravitational lensing reveals the presence of matter, regardless of whether it emits light, making it invaluable for studying dark matter and the large-scale structure of the universe. Gravitational lensing can magnify and distort images of distant galaxies. Some of the most distant galaxies we have ever observed were visible only because gravitational lensing magnified their light. Galaxy clusters act as cosmic telescopes, bending and focusing light from even more distant sources. A single background galaxy may appear as multiple distorted arcs stretched around the lens. This magnification has allowed astronomers to study galaxies that would otherwise be too faint to detect. Gravitational lensing also produces spectacular visual phenomena, including Einstein crosses where a single source appears as 4 images arranged around the lens, and Einstein rings where the source is stretched into a complete circle. These cosmic mirages are beautiful demonstrations of the warped geometry of space-time. Gravitational lensing offers a unique method to study dark matter. Because gravitational lensing depends only on mass, and not on whether that mass emits light, it provides a direct way to map the distribution of dark matter. By measuring the tiny distortions in the shapes of millions of background galaxies, astronomers can reconstruct the dark matter distribution in the foreground. This technique, called weak gravitational lensing, has been used to create maps of dark matter spanning billions of light-years. These maps confirm that dark matter forms an invisible cosmic web, with visible galaxies tracing its densest regions. Strong lensing around galaxy clusters has even revealed the presence of dark matter substructure that would otherwise be completely invisible. Invisible magnetic fields thread through galaxies, guiding charged particles. Galaxies are permeated by magnetic fields that stretch across thousands of light-years. These fields are far weaker than a refrigerator magnet, but extend over such vast scales that they profoundly influence the behavior of charged particles. Cosmic rays spiral along magnetic field lines, confined within galaxies far longer than they would otherwise remain. The fields affect the motions of ionized gas, influencing star formation and the dynamics of the interstellar medium. Galactic magnetic fields are revealed through polarized radio emission and the rotation of polarization angles as light passes through magnetized regions. Though invisible, these fields are essential components of galactic structure. Galactic magnetic fields stretch across thousands of light-years. The magnetic fields within galaxies form complex patterns that trace the structure of the galactic disk and halo. In spiral galaxies like the Milky Way, magnetic field lines often follow the spiral arms, wrapping around the galactic center in sweeping arcs. The origin of these large-scale fields remains a subject of research, but they are thought to be generated and maintained by a dynamo process driven by the rotation and turbulence of ionized gas. Over time, small seed fields are amplified and organized into the coherent structures observed today. These galactic-scale magnetic fields connect regions that would otherwise have no direct interaction. Turbulent gas clouds within galaxies shape star formation. The interstellar medium within galaxies is not calm, but roiled by turbulence on scales ranging from light-years to thousands of light-years. Supernova explosions, stellar winds, and gravitational instabilities stir the gas into chaotic motion. This turbulence influences where and how stars form. Dense regions within turbulent clouds can collapse under gravity to form new stars, while turbulent pressure can also support clouds against collapse. The interplay between gravity and turbulence determines the rate of star formation and the masses of the stars that are born. Understanding interstellar turbulence is essential to explaining why galaxies form stars at the rates they do. Pulsars and distant galaxies send radio waves filling the universe. Radio waves permeate the cosmos, emitted by a wide variety of sources. Pulsars, rapidly rotating neutron stars with intense magnetic fields, beam radio waves like cosmic lighthouses. Active galaxies and quasars emit powerful radio jets that can be detected across billions of light-years. Even ordinary galaxies glow faintly in radio wavelengths, their emission arising from cosmic ray electrons spiraling through magnetic fields. Radio telescopes listen to this cosmic symphony, detecting signals that reveal the presence of objects invisible at other wavelengths. The radio universe is a hidden dimension of the cosmos, rich with information waiting to be decoded. The universe is dominated by matter, but antimatter nearly disappeared. Every particle of matter has an antimatter counterpart with opposite charge. When matter and antimatter meet, they annihilate each other in a flash of pure energy. The Big Bang should have produced equal amounts of matter and antimatter, which would have mutually annihilated, leaving a universe of pure radiation. Instead, the universe today is overwhelmingly composed of matter, with antimatter exceedingly rare. Somehow, a tiny imbalance arose in the early universe, with matter slightly outnumbering antimatter by about 1 part in a billion. After annihilation removed almost everything, this tiny excess remained to form all the stars and galaxies we see today. The origin of this matter-antimatter asymmetry remains one of the most profound puzzles in physics. The Big Bang should have produced equal amounts of matter and antimatter. According to the standard model of particle physics, the fundamental laws treat matter and antimatter almost identically. When energy transforms into mass, it should create particles and antiparticles in equal numbers. In the hot, dense conditions of the early universe, matter and antimatter were continually created and destroyed in pairs. Perfect symmetry would have meant total annihilation, leaving a universe empty of matter. Yet we exist, made of matter, in a cosmos filled with matter. This asymmetry implies that the laws of physics must contain some subtle difference that favored matter over antimatter. Finding this difference is a major goal of particle physics experiments around the world. Why antimatter vanished remains one of physics' greatest mysteries. The disappearance of antimatter in the early universe is known as baryogenesis, and explaining it requires physics beyond the standard model. 3 conditions, known as the Sakharov conditions, must be satisfied for an asymmetry to develop. There must be processes that violate baryon number conservation. CP symmetry must be broken, so that matter and antimatter behave differently, and these processes must occur out of thermal equilibrium. While CP violation has been observed in particle physics experiments, the known effects are far too small to explain the observed asymmetry. New particles and new interactions must be involved, but so far they have eluded discovery. The mystery of antimatter's disappearance touches on the deepest questions about the origin of everything we see. Understanding this imbalance is crucial for explaining why anything exists. If the early universe had been perfectly symmetric between matter and antimatter, mutual annihilation would have left nothing but radiation. There would be no stars, no planets, no life. The slight excess of matter over antimatter, roughly 1 extra matter particle for every billion annihilations, is the sole reason we exist. This tiny asymmetry is the foundation upon which all cosmic structure is built. Understanding its origin is not merely an academic question but addresses why there is something rather than nothing. The search for the mechanism behind this imbalance connects particle physics to the grandest questions of existence. Hypothetical cosmic strings might be relics from the universe's earliest moments. As the universe cooled after the Big Bang, it may have undergone phase transitions similar to water freezing into ice. During such transitions, different regions of space could have settled into different configurations of the underlying fields, leaving behind topological defects at the boundaries. Cosmic strings are one type of such defect, theoretical one-dimensional structures of concentrated energy stretching across cosmic distances. If they exist, cosmic strings would have formed in the first fraction of a second after the Big Bang. They would carry enormous mass per unit length and would affect the geometry of space-time around them. Detecting cosmic strings would provide a window into physics at energies far beyond anything achievable in laboratories. Cosmic strings are theoretical one-dimensional defects in space-time. Unlike ordinary objects, which have 3 spatial dimensions, cosmic strings would be essentially one-dimensional, with thickness far smaller than an atomic nucleus but lengths spanning light-years or even the entire observable universe. Their energy density would be so high that they would warp spacetime around them, creating gravitational lensing effects distinct from those of ordinary mass concentrations. Light passing on opposite sides of a cosmic string would be bent toward it, creating double images of background objects. Despite intensive searches, no definitive evidence for cosmic strings has been found. If they exist, they are either very rare or very difficult to distinguish from other cosmic phenomena. Bubble-like structures may have formed during early cosmic phase transitions. Some theories propose that the early universe underwent violent phase transitions, in which bubbles of a new phase nucleated and expanded. These bubble walls would have collided and merged, potentially leaving observable signatures. Such collisions could have generated gravitational waves that might still be detectable today as a stochastic background pervading the universe. In some scenarios, our entire observable universe might reside within a single bubble that nucleated during inflation. Other bubbles could exist beyond our cosmic horizon, each potentially with different physical constants or laws. These exotic possibilities remain speculative, but illustrate the richness of early universe physics. Detecting cosmic strings would offer profound insights into fundamental physics. If cosmic strings or other topological defects were discovered, they would provide evidence for physics at energy scales far beyond the reach of particle accelerators. The properties of these defects would reveal information about symmetry breaking and field theory at energies trillions of times higher than those produced in the Large Hadron Collider. Gravitational wave observatories are now sensitive enough to potentially detect the signatures of cosmic strings vibrating and decaying. The search continues, driven by the tantalizing possibility of glimpsing the physics of the very early universe frozen into the fabric of spacetime. Cosmic history spans from fractions of a second to billions of years. The story of the universe unfolds across an almost inconceivable range of timescales. In the first tiny fraction of a second, the fundamental forces separated and inflation stretched space exponentially. Within the first 3 minutes, the lightest elements were forged. Hundreds of thousands of years later, atoms formed, and the universe became transparent. The first stars ignited after about 100 million years. Galaxies assembled over billions of years, merging and evolving into the diverse forms we see today. Our own solar system formed about 9 billion years after the Big Bang. Each epoch left its mark on the cosmos, and by reading these marks, we reconstruct the history of everything that has ever been. Scientists measure cosmic history by observing the ages of distant galaxies. Because light takes time to travel, looking at distant objects means looking back in time. When we observe a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. By surveying galaxies at different distances, astronomers can piece together how the universe has evolved. They measure star formation rates, chemical abundances, galaxy sizes and shapes, and black hole activity across cosmic time. Each redshift slice reveals a different era of cosmic history. The most distant galaxies show us the universe in its youth, while nearby galaxies reveal its present state. This light travel time effect transforms the entire observable universe into a time machine. Different cosmic eras left distinct chemical signatures in galaxies. The composition of galaxies changes over cosmic time as successive generations of stars produce heavier elements. The oldest galaxies, formed when the universe was young, contain mostly hydrogen and helium, with trace amounts of heavier elements. Younger galaxies, enriched by billions of years of stellar evolution, contain higher abundances of metals like carbon, oxygen, and iron. By measuring these chemical signatures through spectroscopy, astronomers can estimate when a galaxy's stars formed and how many generations of stellar recycling have occurred. The chemical evolution of galaxies is a record of cosmic history written in the spectral lines of starlight. Cosmic evolution describes how everything changes over billions of years. Nothing in the universe is static. Stars are born, burn through their fuel, and die. Galaxies merge, grow, and eventually exhaust their supplies of star-forming gas. The expansion of space accelerates under the influence of dark energy. Black holes slowly evaporate through Hawking radiation. Even protons may eventually decay over timescales far longer than the current age of the universe. Cosmic evolution is the study of how all these processes unfold, how the universe transforms from its fiery beginnings through its present complexity toward an uncertain future. We are witnesses to a single frame in an epic story spanning trillions of years. The observable universe grows as the cosmic light horizon expands. With each passing moment, light from more distant regions has time to reach us. The edge of the observable universe slowly recedes, revealing galaxies that were previously beyond our horizon. However, the accelerating expansion of the universe complicates this picture. While the light horizon expands, distant galaxies are being carried away by cosmic expansion faster than their light can bridge the gap. Eventually, galaxies that are visible today will fade beyond the observable limit as their light is stretched to infinite wavelengths. The observable universe is thus both expanding and contracting, depending on how we measure it. We are in a unique moment of cosmic history when we can still see the distant light. Brief, powerful bursts of gamma-ray energy light up space for moments at a time. Among the most violent events in the universe are gamma-ray bursts, tremendous explosions that release more energy in seconds than the Sun will emit in its entire lifetime. These bursts come in two main types. Short bursts lasting less than 2 seconds are thought to result from the merger of neutron stars or a neutron star with a black hole. Long bursts lasting from seconds to minutes are associated with the collapse of massive stars into black holes. During the burst, a jet of particles and radiation is launched at nearly the speed of light, producing gamma rays when it slams into surrounding material. Gamma-ray bursts are cosmic beacons visible across billions of light-years. Gamma-ray bursts can briefly outshine entire galaxies. For the brief duration of a gamma-ray burst, the explosion can be the brightest object in the observable universe. A single burst can release as much energy as a supernova, but concentrated into seconds rather than weeks. This concentrated brilliance makes gamma-ray bursts detectable at distances greater than any other transient phenomenon. The most distant gamma-ray burst ever observed came from a time when the universe was less than 1 billion years old, giving us a glimpse of the early cosmos. If a gamma-ray burst occurred in our own galaxy and its jet happened to point toward Earth, it could have devastating effects on our atmosphere. Fortunately, such events are exceedingly rare. Some cosmic uncertainty arises because we observe only one universe. Cosmology faces a unique challenge among the sciences. We have only one universe to observe, and we cannot run experiments on it. This limitation introduces a fundamental uncertainty called cosmic variance. We cannot know whether the particular arrangement of galaxies and structures we see is typical or unusual. Our observable universe is a single sample drawn from a vast ensemble of possible configurations. Statistical fluctuations on the largest scales cannot be averaged away because we have only one sky to measure. This cosmic variance places an irreducible flaw on the precision of our cosmological measurements, a reminder that some aspects of the universe may forever remain uncertain. Cosmic variance is a fundamental limit in our knowledge of the cosmos. Because we can observe only one universe from one location, our measurements of the largest cosmic structures are inherently limited. We see only a finite number of the largest wavelength fluctuations in the cosmic microwave background, and we cannot know whether they are typical. This cosmic variance affects our ability to test theories on the grandest scales. It is not a failure of our instruments or techniques, but a fundamental feature of doing science with a sample size of 1. Cosmologists account for cosmic variance in their analyses, acknowledging that some questions may never be answered with certainty. The universe keeps some of its secrets, simply because we cannot observe enough of it. On the largest scales, the universe looks remarkably uniform in every direction. One of the most striking features of the cosmos is its isotropy, the property of looking the same in every direction. The cosmic microwave background is uniform to 1 part in 100,000. Galaxy counts are the same whether we look north or south, east or west. This isotropy implies that the universe has no preferred direction, no center, and no edge. Combined with the assumption that our location is not special, isotropy leads to the conclusion that the universe is also homogeneous, meaning it looks the same everywhere. This cosmological principle underlies our standard model of the universe. The uniformity we observe is a remnant of conditions established in the first moments after the Big Bang. Matter is distributed evenly on the largest cosmic scales. While galaxies cluster into groups, clusters, and superclusters, these structures become increasingly rare on larger scales. Beyond a few 100 million light-years, the distribution of matter smooths out. There are no galaxy walls, filaments, or voids larger than a certain characteristic size. The universe becomes homogeneous, with the same average density of matter in every sufficiently large volume. This transition to uniformity is a key prediction of the standard cosmological model and is confirmed by observations. The cosmic web is the largest pattern in the universe. On scales beyond it, the cosmos is smooth, simple, and endlessly repeated. The grandiose structures we see are merely local perturbations in an otherwise uniform sea of matter and energy. And now the vastness of the cosmos begins to gently fade behind your thoughts. You have drifted through 100 quiet wonders. From the dazzling brilliance of newborn stars to the silent shadows of ancient galaxies. From the intricate web of dark matter to the faint whispers of cosmic background light. You have traveled through starry nurseries, soared along luminous spiral arms, and glimpsed the heart of the universe glowing softly across unimaginable distances. You are part of this cosmic story. Not just an observer, but a participant woven into the fabric of stardust and time. The atoms in your body were forged in the fires of ancient stars. The air you breathe carries the legacy of distant explosions. Everything within you shares a lineage with the universe itself, born from the same primordial matter that now flows through galaxies and drifts in interstellar clouds. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the slow pulse of distant pulsars, like the patient expansion of space itself. Tonight, as you rest, the cosmos continues its quiet unfolding. Stars are forming, light is traveling, and cosmic dances carry on in silent harmony. You are a small, warm presence within this vast, radiant sea. peacefully floating among the stars. Sleep well. Sweet dreams. And may you carry with you the quiet knowledge that you are made of stars, drifting gently through a universe that has been unfolding for nearly 14 billion years. Thank you for joining me on this journey through the cosmos. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the universe. There are more wonders waiting. More mysteries hidden in the darkness between galaxies. More secrets to drift through on quiet evenings. Rest well. And may the silence of space keep you company through the night. This has been Drowsy Discovery. Good night.